So, in my last lecture I started module 6 that is power distribution system planning, different models and solution strategies. Okay. So, basically in my last lecture I gave you an overview of different planning models available in the literature. Okay. And in order to make you understand these different planning models, I gave a brief overview on basics of optimization and particularly what are the different types of optimization problems possible, those things I discuss in brief. Okay. So, also at the end of my last lecture I discussed the formulation of a typical distribution system planning problem. Okay. And that is basically single objective optimization problem, which means that we have one optimization objectives which we need to optimize under certain technical constants. Okay. So, if I go to this my last lecture, you can see here we have shown that objective function formulation, and as I said, although here we have formulated two objective functions, but actually we have one objective function which we will consider at a time. That means, I have presented two different planning problems, two different planning models. In one model, that is in problem 1, my objective function is total of installation and operational cost or total investment on operational cost, or in fact simply total cost, which is basically sum total of all the cost components involved in a typical distribution network planning or design. Okay. So, this objective of course, we will minimize, this is a minimization problem. So, basically every time we know that we optimize the cost, we minimize the cost in order to enhance the economy of the design network. Okay. So, this cost is optimized in order to improve the or in order to enhance the economy of the network, or in order to have an economical solution. By optimizing this cost function, we will get an economical solution. Okay. That I have mentioned. And the second problem, and this of course, it is a constant optimization problem. It means that we will optimize this cost function under certain constant. Those constants I discussed in my next slide. So, this problem 1 is minimization of this cost function under these constants. We have 1, 2, 3 constants, and also in addition to that we have radiality constants. So, this is radiality constants. Okay. Similarly, this is what this problem 1 or case 1. Okay. Similarly, the second planning problem is to minimize this other objective, which is I mentioned next, that is the total interruption cost, by minimizing which we can maximize the reliability network, or by minimizing that this objective function we get a solution which would be reliable solution. So, this our goal is to have reliable solution by solving that particular problem. So, second problem is to determine the a reliable network, and the first problem is to determine the economical network. So, this thing you have to clear. So, in fact, the second problem was to minimize this interruption cost or to maximize the reliability for under this constant. So, that we get reliable solution. Okay. And in the first problem we minimize this total cost under these constants, that is equality and inequality constants, to have an economical solution. So, that is the thing that you should understand. Okay. In fact, all these technical constants which I described in my last lecture are applicable for both the problems. Okay. Only objective functions will change, but constants will be same for both these problems. Now, we have to verify this planning problems under certain system. Okay. And here we have taken 4 test system or 4 test networks. One is a 21 node system, that means that system or that network is having 21 load nodes or 21 number of nodes, not all are load nodes, but we have total 21 numbers of loads or buses, 21 numbers of nodes or buses. The second problem is having 54 nodes, a network having 54 nodes. The third problem is a network of having 100 nodes or 100 buses, and the fourth problem is a network with 182 node system. Okay. But we have many differences in these 4 systems, they are not identical. So, these systems are not identical, that you have to understand. These networks or systems are not identical, that is one has to understand. So, we have to understand that we have formulated this objective function in a generalized manner, but these problems are of different. Okay. What are the differences? Now, 21 node system and 182 node system, these two are examples of expansion planning problem. Expansion planning problem. As I said, there are 2 types of problem possible. One is static planning, another is dynamic planning. In dynamic planning, we have a category where we need to expand the network. We have some existing network which needs to be we have some pre-existing networks which need to be expanded with some additional nodes or additional load points. Okay. But this 54 node and 100 node system, these are examples of static planning. Static planning for a brand new network, for a new network. So, here in this case, this expansion planning problem in for 21 node and 182 node systems, we have some pre-existing infrastructure, pre-existing network or infrastructure. Okay. But here for this 54 node and 100 node system, we do not have we do not have any pre-existing network, and we are supposed to build a brand new network. So, no pre-existing network. Okay. So, there are some differences. So, let me discuss this problem one by one. Let us start with here you can find some highlights of this test system. As I mentioned, 182 node system, basically we have 2 substations. Other than that, we have only one substation for all other network. Okay. and also for 21 and 182 node systems, we have some existing networks, as I was talking about in the last slide. So, hence they need expansion planning. But for 182 node system, we have two substations. They are located at node number 181 and 182, and we have also some pre-existing networks which we need to expand with some additional node points. Okay. So, let us start with this 21 node system. This 21 node system is having these black dots. So, these dots represent load nodes, where we have some load demand or load nodes or load buses. Okay. So, here we have some load demand, and this symbol is representing the location of substation. Location of substation. So, here you can see here we have at bus number 1, we have substation located. Okay. And this is a single feeder network. So, this is a single feeder network which is pre-existing. So, this node numbers are shown within bracket. So, this 1 or this 2, this represent node number. All right. And this line represent this distribution, this line, thin line, this represents distribution line or branch, whatever you can call. In some paper they have considered, I mean they have mentioned this as a branch, and in some paper they have written as line. So, what do you mean by line? Again it is the connection of the two neighboring nodes or two neighboring buses. So, we have a one line between node number 1 to node number 2, we have another line between node number 2 to node number 3, and similarly we have another two lines, one is node number 3 to 4 and one is node number 3 to 5. Okay. So, in between these two nodes we have one line each, and in every line there is an italic numeral. You can see 1, 2, 3, 1. This basically represents this italic numerals at lines represent conductor size, conductor type or conductor size. I will show you that a conductor table where there are a set of conductors which are in fact differentiated with conductor type 1, type 2, type 3, type 4 or size 1, size 2, size 3, size 4 and so on. Okay. So, these 3 represent that this line which is connecting node number 1 and node number 2 is built with a conductor type 3. Okay. So, I can write it again. So, these 3 represents the distribution line connecting nodes 1 and 2 is built with is built with conductor type or conductor size, whatever you can call 3, conductor type or conductor size 3. Okay. So, now we have, you can see we have this pre-existing network. So, this is pre-existing network, okay. And we also have this new load points or new nodes. Okay. So, we have a pre-existing network which consists of this bus 1, bus 2, bus 3 or node 1, node 2, node 3, node 4, node 5, and we have some new nodal points, some new load points starting from node number 6 to node number 21. Now, our goal is to connect all these new load points with this pre-existing network with an optimal way, okay, with an optimal way. Now, of course, you can understand this needs an optimization problem to be formulated, and we have formulated 2 optimization problems here, which I have shown you in my last lecture. One is we should connect this new load points to this pre-existing network such that we get an economical network, we get an economical network. Okay. And the second problem you have seen that we will connect this new load points or new loading points to this pre-existing network in such a way that we will get a reliable network. So, I can write it here. So, now, our goals are number 1, that is problem 1, to connect the new load points to the pre-existing network so that we get an economical network. Okay. And in problem 2, everything is same. Here also our goal is to connect all these new node or new load points to the pre-existing network, but here our goal is to find a reliable network. So, instead of economical network, here we are intending to have a reliable network. Okay. So, that is what the difference between this problem 1 and problem 2. Okay. All right. So, I hope that this is understood, and that is why, since we are intending to connect this new load points to this pre-existing network, that is why we call this planning problem as expansion problem. So, this is an example of expansion problem, because ultimately we are expanding a pre-existing network by connecting with so many new node points. Okay. So, that is something one needs to understand. Now, these are the data of this 21 node system, I will give the reference from where we get this data. Okay. In my list of the references, you can find from where we get this data. So, here you can see we have in this table we have some columns. So, column A is basically representing this index of nodes, node 1, node 2, node 3 up to node 21. Column B is representing this type of the node. Okay. So, node 1 is of one type, that means it is for substation, and other all nodes starting from node 2 to node 21 all all entries are 0, means that they are load nodes. That means that we have some loads connected to this node. Okay. And column C and D represent this north coordinate and west coordinate of the node. So, this is basically shown over in my last slide. So, suppose this is your coordinate system. So, basically all these nodes are located within this coordinate system, and this is north and this is probably west coordinate. Okay. So, each of these starting from the substation, all these nodes are physically located in this coordinate system. Okay, in this coordinate system. So, it means that for node 1 this node is located this is of course, I think it is in kilometer, it is in kilometer. So, that means this is located 1 kilometer north west starting from the reference point. So, this is suppose reference point 0 0. So, this is basically the location of 1 comma 1. Okay. So, with this physical coordinate system you can find out the distance between these two nodes. So, you can easily find out this what is the distance between these two nodes, what is the distance between these two nodes, and so on. So, what is the distance between these two nodes. So, this you can find out with this coordinate system, that is from C and D. Okay. And E and F represent this power demand. So, this represent power demand of nodes. So, you can see that since you know that node 1 is at it is substation, so or it is slack bus or slack node. So, power demand is written over 0 0, and but all other nodes having some finite power demand. For example, node 2 is having 200 kilowatt of active power demand and 50 kVAr of reactive power demand. But remember, this is a planning problem, and this kilowatt and kVAr basically representing peak load demand. So, we always as I mentioned at the module 2 that we design a network by considering peak load demand, Okay. So that the whatever network we will be getting after executing this optimization problem, this network should be should capable of supplying this peak load demand. So, that is what the goal, and all this planning process subsequently all these test systems the planning or to design a network we consider the peak load demands. Okay. And that peak load demand may be a projected peak load demand for next 10 years or maybe next 15 years, depending upon what type of planning horizon you have chosen. So, it is of course, not the peak load demand at this present time, because we build a network, we design a network considering a certain planning horizon. Already I mentioned in my last lecture that we build a network by considering a planning horizon. So, if planning horizon is let us say 10 years or 15 years. So, we build a network so that it can capable of supplying all its demand nodes up to next 10 years or up to next planning horizon years. Okay. And this column G is basically representing importance level of the node. So, this is something that it is used to specify that some nodes are of different types of nodes, but eventually you can assume that we will not consider it at the moment this importance level, but of course, if you have some different types of loads like these hospitals where we have some dedicated equipment connected. So, we need some special attention for that. If we have some air traffic control system in a network, we need some special attention. So, those based upon that this importance is decided, and column H specify this substation voltage magnitude, which is in per unit, Okay. Now, this table gives you the different types of conductor sizes, As I said, this in normal planning, what usually planners do, we have a set of conductor types or set of conductor sizes from which we need to select one specific type of the conductor or one specific size of the conductor for constructing a distribution line. Okay. And here we have 9 different types of the conductor, all can be out of which one can be used to construct a particular line. That means, if I want to construct a distribution line between node 2 to node 3, I need to take the decision that what type of conductor I should use. Okay. And you can see here we have a set of 9 different types of conductors. So, I can use either 1 or 2 or 3 or whatever, that basically depends upon different things, that what should be the tentative power flow through this particular line, and also that depends upon the economy of the solution, that depends upon how much reliability do we need to construct this line. Now, corresponding each of this conductor type, you can see this row is basically representing this all the specification of this conductor type 1. Okay. So, here it is the first second column is basically representing this current rating or ampacity rating or ampacity limit. This is ampere capacity limit or thermal limit, you can say, or thermal limit. Okay. That means, this if you build a line with this conductor type 1, maximum current that should flow through this line should be limited to 118 ampere. Okay. Similarly, corresponding to this conductor type 1, the resistance of the conductor is given to be 1.6118 ohm per kilometer, okay, and reactance is also given 0.4853 ohm per kilometer. And next 3 columns gives the cost component, cost coefficient, because as I have said that we need some cost coefficient in order to estimate the cost of installation of a particular line, and these 3 are the cost coefficients. So, this one is installation cost, branch or line installation cost, this one is preventive maintenance cost, and this one is corrective maintenance cost. So, these 2 are maintenance cost and this is installation cost. In fact, you can see in the problem formulation we have this cost coefficient C. C is basically cost coefficient for installation cost, and C I is basically representing the cost coefficient for installation cost, and C M is basically representing the cost coefficient for maintenance cost. So, this we can obtain from this conductor table. Okay. And these last 2 are basically representing reliability data. reliability data. As you know, in my third module, I explained that in order to assess, in order to estimate the reliability of a particular component, we need two data. One is called failure rate, another is mean failure duration. Okay. So, these data are provided over here. One is 0.2 falls per kilometer per year, one is 0.33. Okay. All right. Now, similarly for all other conductor type, this is specified, this all informations are specified. Now, you can see the difference from one type of the conductor to the other type. So, conductor 1 is having ampacity of 118 ampere, but conductor 2 is having ampacity of 158 ampere. Okay. Now, what is the difference of these two? It means that conductor 2 can withstand higher amount of current. How it is possible? Because its conductor cross sectional area is higher, okay? And that is why its resistance is lower, reactance depends upon this line construction, and since this conductor cross sectional area is higher, its cost is also higher, both installation cost, only installation cost, but maintenance cost almost same, and failure rate and repair duration are also not dependent upon this cross sectional size of the conductor. Okay. Now, you can look at from conductor type 1 to 7, we have specific say types of the conductors built with specific materials, and that is why their failure rate and repair duration are similar or same. But conductor type 8 and 9 are different. So, conductor 8 is having ampacity of this and 9 is having higher ampacity, but their failure rate and repair duration are significantly small. Okay. So, for example, you can understand that it might be that conductor type 1 to 7 are all overhead conductor and conductor 8 to 9 may be underground cable which is having lower value of failure rate, but mean failure duration is also lower. It might be underground cable or might be built a conductor is having superior reliability parameters. Okay. All right. Now, this was all about 21 node system. For 100 node system, it is an example of a static planning, and it is an example of building or designing a brand new network, and that is why you can see substation is specified at this node 1. So, here we have substation located, and you can see apart from this location of the substation which is already mentioned, which is already specified at node 1, there is no pre-existing network, So, we have to connect all these different nodes or loading points to this substation in order to build one brand new network, and that is to be done by using this optimization approach, okay, or by using this planning approach. So, it is an example of developing a brand new network. Okay. It is an example of developing a brand new network. So, this is 54 node system, it is also similar to 100 node system. Here we do not have any pre-existing network. So, similar to the previous one, it is also a system to develop a brand new network, where substation location is not even specified. So, the characteristic of this 54 node system or the difference of this 54 node system with the 100 node system, although both of them are same type, like both of them are the example of planning a brand new network, but here we do not have specified substation location. So, we do not have specified substation location. Okay. And these are the coordinate systems. This information related to their respective position of all these nodes are specified, from which you can eventually find out the distance from one node to other. Okay. But for this 54 and 100 node system, we have used only two conductor type. One is conductor type 1 and type 2. Okay. So, type 1 is having ampacity of 150 ampere and type 2 is having ampacity of 230 ampere. Okay. This is purposefully done in order to reduce the problem dimension. Okay. I will explain later on, because compared to this 21 node system, here we have more number of nodes. So, more number of decision variables involved, and this increases the problem dimension. Okay. For 100 to 82 node system, we use these two conductor size. One is having ampacity of 255 ampere, another is ampacity of 515 ampere, and their respective cost and reliability data are specified. This is cost data, this is reliability data are specified, and we need to build a network by with these two conductor sizes. Now, 182 node system is not shown over here. I can show you, I have some illustration here. So, this is 182 node system, where you can see these bold lines. So, bold lines represent the pre-existing network. Okay. So, here at 182 node, at node number 181 and at node number 182, we have substation. So, these two are substation. Okay. And substations locations are specified at node number 181 and node number 182, and in node number 181 we have some pre-existing network, but node number 182 we do not have any pre-existing network. So, our goal is to connect all these node points, either to connect this pre-existing network where substation is located at 181, or to connect this substation 182. Okay. So, that is what we have done through this optimization. Now, we, as already we have mentioned, that we have formulated two planning problems, two single objective planning problems, where the difference between these two problems is that in one problem we have objective function as total cost, and another problem we have objective function is of total interruption cost, or it is related to maximization of reliability. Okay. And we both the optimization problem we will solve separately, and in order to solve this optimization problem, we need to have one solution strategy, and here we will use PSO. PSO stands for particle swarm optimization. So, this is a meta heuristic optimization algorithm, which we will use as the solution strategy for this two planning problems. Okay. Also, I will talk about particle swarm optimization after a little while, and you will see that it is a kind of meta heuristic algorithm, which can solve any type of optimization problem, whether it is linear or non-linear, does not matter to it. It can solve convex or non-convex problem, or differentiable non-differentiable problems. It can solve any problem, but the drawback is that the convergence, that the solution at the end we are getting, which we are thinking that it is a optimal solution, that optimality is not guaranteed. And since it is a meta heuristic algorithm, it will can provide you different solution if you make different simulation runs. And that is why whoever will be using this particular algorithm, meta heuristic algorithm, needs to work with some more statistics to statistically show the performance, okay? And that is what exactly is done in this particular case. I will be discussing. And apart from that, we will be using a novel encoding decoding scheme for PSO, which I will be explaining after a while, and also we will be using a branch conductor or line conductor site selection algorithm as a support subroutine of the main solution algorithm, so that we can decide, or we can take the decision that what should be the conductor size for each of the line that we are going to construct. Okay. Now, why we have taken PSO? PSO, many people will not agree that this is an evolutionary algorithm, but this is a population based meta heuristic algorithm. So, I can rename it population based meta heuristic algorithm. Rhythms. So, the idea was that motivation for selecting PSO was that time whenever I worked on this, was that PSO was not used for distribution system planning problem, but PSO has one attractive feature that it can be easily implemented. Although easy is something a vague word, means something which I can tell you as easy, but cannot be easy to someone else, but eventually if you implement many of the such kind of meta heuristic algorithms by yourself, you can realize that PSO needs a few line of coding to implement. Okay. So, that is indeed easy to implement, and also effective memory use, less memory use, and ability to deliver solution with less number of function evolution. So, those things you can identify if you go through the literature of different types of meta heuristic algorithms. And that time when I worked on this genetic algorithm, this is again one meta heuristic population based meta heuristic algorithm under this category of evolutionary algorithm was more popular, and it was extensively used to solve this distribution system planning problem. So, idea was that if we implement PSO, we can make a performance comparison. Okay. Now, how PSO works? So, PSO is a population based algorithm, that means it is a multi point search technique. Now, what is that? Basically, the iterative algorithms can be classified into two types. One is point to point search technique. It means that you start with any initial guess and then you update it in the next iteration. But this PSO or maybe genetic algorithm, these are population based search technique, and that is why they are a multi point search technique. So, they will start with multiple initial solution, all the solutions will be randomly generated, and these solutions will be iteratively updated to have a base solution at the end. At the end also we will get a set of solution, among them we have to select the best solution, and that is what we consider to be the optimal solution. So, we have a population based search technique, it is, and each potential solution is called as particle. So, each particle is basically in particle sum optimization represents a potential solution, which may be a decoded solution or which may represent direct solution. That depends upon how you are encoding decoding the problem variables. If you are encoding decoding is direct, then you get whatever particle you get, that represents a direct solution. Otherwise, you have to decode the information from this particle to have this final solution. And each particle is encoded by a position vector. Then this position vector will be updated by the velocity in the successive iteration, and this velocity is finally updated with two equations that I am going to show you in the next slide. One is called velocity updatation equation, another is called particle updatation equation. Velocity updatation equation is done by considering this particle previous based value and a group leader based value, or the global or the group based value. Okay. So, the idea behind this velocity updatation is that when we have some athletic competition. Okay. For example, we have some 100-meter race. Now, how a competitor can win? If that competitor exceeds his or her previous best, as well as if he can perform better than all other competitors. Okay. So, that is what the motivation. And this particle sum optimization is was developed 1995, I think, by Kennedy and Eberhardt. Okay. And that paper was cited many times. Okay. And these are the two equations. This equation is basically for velocity updatation equation, velocity update equation, and this equation is basically position update equation. And as I said, these are basically the basic PSO variant, which was proposed by Kennedy Eberhardt, and subsequently this basic update equation was modified or revised by different authors, and we have different PSO variants as well, depending upon this change in this updatation equation, or by incorporating different features in it, we have different PSO variants. Until today, people are working on it to have a better PSO variant. Okay. So, here you can look at this equation, this u, capital U I j iter plus 1 stands for this is the velocity for ith particle jth dimension. Okay. So, that means this is for ith particle jth dimension, but means this is for jth decision variables. In fact, one particle consists of many decision variables. So, this is basically the ith particle jth decision variable. Okay. And this is updated with this information of previous iteration velocity value, and plus by adding these two terms. One is this term is basically to update its own previous based value, which is representing this by p base. P base is, you can see, the best position of that same particle, same dimension previously, and this g best is basically representing the global based or the leader based information. Okay. So, this is basically how this velocity of one particle is updated with its own previous best and with a global previous best. Okay. And how we know that this p best and g best, this is basically done with the evaluation of one function by comparing two particles by one function, that is called fitness function. Okay. Those who have a fair idea on this such kind of population meta heuristic algorithm, they can understand, and this fitness function is eventually derived from our objective function. It can directly represent objective function, or it can be some modified form of the objective function. Okay. And there are many other parameters which I am not going into detail, like this phi 1, phi 2 represent learning constants. These are random numbers r n 1, r n 2, and this S is basically representing this position of this ith particle, jth dimension means jth decision variable. So, the second equation you can see that one particle position to next iteration is updated with the previous iteration position value by adding this new iterations velocity. Okay. And since that position is updated with previous position plus velocity multiplied by this time, here you can see the difference between the one velocity and other velocity, the time difference is iter plus 1 minus iter, that is equal to 1. Okay. So, that multiplied by 1 is basically the position update equation. Now, we have different PSO variants. So, what I can tell you that how this PSO works, although we have this equation pseudo code for this PSO, but I can tell you that in general this PSO first algorithm flowchart is something like that. First you start this algorithm, then you initialize. Before that you set this iteration count or maximum iteration max and population size. Okay. So, these are the two parameters, like there are several parameters in forward backward sweep load flow. So, similar to that, to these two parameters we have to set at the very beginning. Okay. Then we have to initialize the solution, initialize this particle population. Lies population, particle population. Okay. So, once you have done it, then you start with iteration 1, and then you have some conditions that whether it is exceeding this maximum iteration or not. This iteration is higher than equal to that maximum iteration, for example, it is iteration max. If yes, then you terminate, end. If no, what you can do? You update population. How do you update? This update equations already I have shown you. This is how we can update. Okay. And after updating, you make this iteration count iter plus 1. Okay. Once you get that, you again go back to this main loop. Now, here if it yes, then it ends, if no, it will keep updating. In fact, this is the basic equation, but one can obviously change this algorithm by suitably revising some of the things. Okay. Now, we have used 3 PSO variants. We have as I mentioned, in one is PSO with constriction factor, where one factor is multiplied with this velocity update equation, okay, and that factor may have some constant value or some time means iteratively changing value. Similarly, second variant is one inertia weight is multiplied with this velocity, and that inertia weight the idea is to make the balance between local and global search. Okay. Too many consideration of too many preference of this previous base will make entrapment into local optima. So, in order to come out from that, we need to have some balancing of this local exploration with global exploration. Okay. Similarly, we have another variant which is called comprehensive learning PSO, in which each dimension or each decisions are updated separately. This will not follow this in general velocity update equation which I have shown over this slide, but this is use the separate velocity updation equation for different decisions variable or different dimensions of the problem. Okay. So, this is the pseudocode of this mono objective planning problem. Initially, we set this population size, or that means how many number of particles we should utilize in the search process, and also maximum number of iterations. Then if you have some encoding technique that we use for that encoding decoding technique to encode the solution and to get the direct information with the decoding value. Then we have this loop, this is the main loop by which we will update this velocity and position vectors, okay, and we update them, we preserve this previous best velocity, we preserve this the best solution among all the particle, all this will come under LT strategy, and this will continue till we get this maximum iteration arrived. Okay. So, this is here the termination criteria is maximum iteration, but again one can change the termination criteria as well. This is a special type of encoding decoding technique, encoding decoding scheme we have used. Instead of designing direct information, we have some indirect encoding technique, where we have some it is called cost biased encoding technique. So, each of the nodes which need to be connected with the new network will have some bias value, and this bias value will be updated iteratively, and from this bias value with a suitable decoding scheme which is mentioned over here, which is called cost bias decoding scheme, we get the a total network topology or total network structure of a network, and that will make your radiality constant satisfied. Okay. It always gives a radial network. So, I will not discuss this in detail. If you have further interest, you can go through this algorithm. Okay. Also, this is how we can select the conductor size. We for each of the branch we assign some set of conductors, then we also make some heuristic idea. So, that for each branch or line, this line capacity constraint would be would not be violated. Okay. So, this is how it is formulated. So, you can go through this algorithm, and this is how these other constants are handled in this particular problem. We have many constants. So, power balance constant is automatically handled by forward backward sweep load flow. Capacity constant is substation capacity is chosen as per the load demand. Similarly, branch capacity is satisfied with this conductor size selection algorithm or conductor size selection subroutine. If voltage limit is violated, then we have some penalty factor which needs to be added to penalize the solution, and radiality constant is always satisfied by the proposed decoding scheme, which I was talking about. Now, these are the solutions we got. Before we got the solution, let us you can see both the problems are solutions of both the problems are shown in the same graph. This is A is for 21 node system, B figure B is for 54 node system, C is for 100 node system, and D is for 182 node system. Okay. And here this is basically representing this solution that we will get in problem 1, and this is for problem 2. So, as all this graph you can see. Okay. And this is basically representing, this graph is basically representing how this cost function, how this objective function varies with this number of iterations. So, here we have set 100 number of iterations as maximum iteration. For 54 node systems, if problem dimension is higher, so we set higher number of maximum iteration, that is 300. For 100 node system also we consider 300, 180 node system we consider 300. Again, how do you choose this population size and maximum of number of iteration? This is again you need to some statistical, and you need to do some statistical analysis by changing them, and by suitably doing this sensitivity analysis. Now, you can see all these characteristics are in general same. So, initially cost was higher, then it becomes lower after certain iteration and then it gets saturated. When it gets saturated, we can understand that the solutions are not getting updated, which means that no better solutions we are getting. But again, as I said, these are all involve some randomness. So, we need to do some statistical tests. So, here we need we did many statistical tests which are not shown over here. Here we have used box plots to represent what the variability that we get in the final solution. Okay. So, this box plot is used basically to compare the performances of these three different PSO variants that we have studied, and out of which you can identify by yourself which one is better, okay, which one will have less variability as well as less median value. And these are the final solutions we get. Here we have shown this here most economical solution which we get from problem 1, and this is most reliable network which we get from this problem 2 by solving this problem 2. So, problem 1 objective was minimizing cost and problem 2 objective was maximizing the reliability. So, here you can see the difference between these two. Here you have more number of branching which requires that dependingness of one node to other, which reduce the dependingness. Also the conductor sizes are different. Here conductor type 9 is used, so that we have better reliable network. Whereas, in this most economical system we have almost shortest path network, meaning that the total cost that it will incur will be less. So, similar things we observe for 54 node system. This is we got most economical network we got by solving this problem 1, and most reliable network we got by solving problem 2. Okay. So, similar observations you can get with what we get in previous. Similarly, this is for most economical network by solving this problem 1 for 100 node system. This is a kind of shortest path problem, shortest path network, but here this is what we get from 100 node system by solving this problem 2. Okay. Here different conductor sizes is used, also different more number of branching is there. Similarly, this is we got from 182 node system by solving this problem 1, that represent this economical network, and this is what we get by solving this problem 2, that is the reliable network. Okay. And the observations are also similar. Previously, it is a kind of shortest path network, whereas you can see there this is not. Okay. And also this conductor sizes are of different. Now, with this I will stop in this lecture, we will proceed further in the next lecture. Thank you.